Hello, welcome to this video. In this video, we will learn application of steady flow energy equation, or we call it as SFEE. This is nothing but first law of thermodynamics for an open system. We can apply the first law of thermodynamics for an open system for any of the steady flow device like boiler, turbine, compressor, pump, nozzle and diffuser, and also throttle valve. So let us start from SFEE general equation, which we already know. So SFEE is given by Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. And if you expand it, dH is H2 minus H1 and change in kinetic energy is half into V2 square minus V1 square plus G into Z2 minus Z1. This is what we already know. Now, let us start with a boiler. Do we know what boiler exactly mean? Boiler is a steady flow device in which the boiler which we are talking here is a boiler which is used in a thermal power plant where heat is added and water is getting converted into steam at constant pressure. So, in a typical boiler, what we will have is heat is being supplied, and you have inlet as water which is mass coming in and steam is going out. So, let us start with the general equations as we already know. Now, in a boiler, as we said, it is not a device which produces work. There is no work interaction in this device. So, work transfer can be neglected. Alright. In boiler, there is negligible kinetic energy change. Boiler is not a device like nozzle or diffuser where there is a significant change in kinetic energy. So, this also can be neglected. So, we are neglecting work transfer because there will not be a work interaction in a boiler, and we are neglecting change in kinetic energy because boiler is not a device where the kinetic energy change is significant. And this Z2 and Z1 is the distance from the reference point, the inlet and outlet. So, we can compare to the other energy transfer, this will be generally negligible even though there is small difference in height, this will be generally negligible. Or we can say the inlet and outlet both are at the same level. The moment Z2 is equal to Z1, this will also become 0. Therefore, the heat transfer in a boiler is given by H2 minus H1. So, this is what a simple equation which we can reduce. And remember, the actual condition may differ because in some cases he may give you the values of Z2 and Z1, then we will consider in that case. But if you are trying to simplify, the simplest form where neglecting all other forms of energy will be Q is equal to H2 minus H1. And one more thing which we can note down here is energy H2 is enthalpy. Enthalpy is U plus PV. So, by adding the heat, that means you can say that H2 is enthalpy at outlet, H1 is enthalpy at inlet. So, enthalpy is nothing but the other form of energy because you have internal energy and flow energy. So, if you add the heat, H2 will be greater, H1 will be lesser. So, we can say here H1 will be lesser than H2. So, we can say this will be positive. And we also know Q is positive for heat added. So, that is correct. Okay. So, this is the application of SFEE for a boiler. Now, let us move on to the next device which is a turbine. Now, how do we represent turbine? So, in a simple line diagram, turbine is an expansion device where volume is increased from inlet to outlet. So, this is something like inlet, this outlet. So, mass is coming in here and mass is going out here. So, what we can say here is generally the turbines are walls are insulated, that should be the case, it should be adiabatic, alright. Okay. Now, let us start with the same equation which we already know, Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. and we have assumed that Z1 is equal to Z2. So, this term becomes 0, negligible change in potential energy because both inlet and outlet are at same height, or compared to any other form of energy transfer, this is negligible. And this is not a device where kinetic energy change is significant. So, this also will be equal to 0. If it is given, we will consider it later, but for an ideal case, we will assume that there is not significant change in kinetic energy. And this is not a device where heat is assumed to be, or heat is allowed to be transferred out of the system. So, Q transfer or heat transfer is also 0. Then what we will have is minus W is equal to H2 minus H1, or we can say W is equal to, if we send that negative sign this side, it will W is equal to H1 minus H2. Now, we can also see whether this work interaction will be positive or negative. Let us check here. H1 will be enthalpy of the steam at the inlet, H2 will be enthalpy of steam at outlet. So, we can know that energy at inlet will be higher in a turbine. Steam is the working fluid. Steam's energy at inlet will be higher. So, H1 will be higher, H2 will be lesser. Since H1 is greater than H2 here, you can conclude that the work transfer which we are going to get will be positive. And we know work transfer will be positive for a turbine because it is a work producing device. Alright, because H1 is greater than H2, we can say W is positive in a turbine. Now, let us move on to the next device, which is a compressor. Generally, compressor is represented with a symbol like this, which is reducing in area. This is our inlet. So, mass is coming in, mass is going out. Now, what is a compressor? Compressor is a steady flow device in which pressure of the gas is increased. Okay. So, volume is obviously decreased. That is why it is shown in a such symbol. So, this is where mass is coming in and this is where mass is going out. Now, compressor is a device which is assumed to be no heat interaction, but work is done on the system, because if at all we are compressing some gas, work is given in the form of electrical energy or in the form of some piston work. So, this will remain same, minus W is equal to, now this H2 minus H1 will be there, and this is not a device where kinetic energy change is significant. Assuming that inlet and outlet both are at same height, we can conclude that this is also 0. Now, W can be written as H1 minus H2. Okay. Now, W is H1 minus H2. Will it be positive or negative? Let us check. This is our H1, this is our H2. Now, if we are compressing, you see, after compression, because you are giving work to compress. So, after giving work, H2 will be greater. So, energy of the gas will be higher here. Energy of the gas at inlet will be lesser. So, what is our conclusion? H1 is lesser than H2. So, therefore, H1 minus H2 will be negative. So, work transfer is negative. When work is given to the system, work will be negative. So, that is correct here. So, work for a compressor will be negative. Now, let us move on to the next device, a pump. So, there is not much difference between a compressor and pump in terms of this reduction of steady flow energy equation. Pump is handling water or liquid, whereas compressor is handling gas. Now, let us come back from the same equation. Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Now, as usual, we neglect this Z2 minus Z1 is equal to 0. Change in kinetic energy is also negligible, and pump is a device where heat transfer is negligible. So, minus work transfer will be equal to H2 minus H1. W is equal to H1 minus H2. Now, this is as same as the last. So, we are giving work, whereas H1 is lesser here, H2 will be higher. So, what is our conclusion? H1 is lesser than H2. So, W will be negative. So, it is a work absorbing device. So, obviously, work transfer will be negative for a work absorbing device. Now, what is a nozzle and diffuser? This is the case where things get interesting. Let us start from the same equation. Q minus W is the change in enthalpy plus change in kinetic energy plus change in potential energy. Okay. Nozzle and diffuser is a device where nozzle converts pressure energy into kinetic energy, where on the diffuser converts kinetic energy into pressure energy. So, both derivation will be same. So, heat transfer is negligible in a nozzle or diffuser. Work transfer is negligible. There is not much change in potential energy, assuming that inlet and outlet are at same level. Now, what will remain with is only these two terms. So, this H2 minus H1 and this change in kinetic energy is half into V2 square minus V1 square. Now, in nozzle or diffuser, we may be pretty much interested in velocity at the outlet. So, let us reduce this to velocity at outlet. Now, what will happen to this? This will come on the other side, H1 will be positive minus H2 half into V2 square minus V1 square. Or this 2 will go here, 2 into H1 minus H2 is equal to V2 square minus V1 square. Or we can say V2 square, I will simplify this for V2 square, 2 into H1 minus H2 plus V1 square. Or we can also write V2 is equal to square root of 2 into H1 minus H2 plus V1 square. In some cases, velocity at the inlet will be negligible. In that case, if inlet velocity is negligible, we can rewrite this equation square root of 2 into H1 minus H2. That's it. And very important, the unit of this has to be in joule per kg. H1 in joule per kg to get velocity in meter per second. Very important. Now, throttle valve. A throttle valve is a device, steady flow device of course, which reduces fluid pressure through restriction. So, there is a restricted valve here. So, there is no heat transfer and work interaction of course, and he is already stated that it is a constant enthalpy process. Now, let us reduce it. Delta Q minus delta W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Alright. Now, this is a device, throttling valve is a device where pressure is reduced, that is it. So, Q is equal to 0, there is no work transfer in this device, there is no significant kinetic energy change, there is no change in potential energy, all you will remain with is change in enthalpy. So, H2 minus H1 is equal to 0, or you can say that H1 is equal to H2. So, that is what we said, it is a constant enthalpy process. Enthalpy remains constant for a throttling process. So, what we have seen from these derivations, it is important to understand the working of these each devices in order to reduce steady flow energy equations. That will help you to derive it easily. Thank you.